In this example, we're asked to come up with the inverse of the stiffness matrix for the 3 degree of freedom system that is shown. We have absolute coordinates of x1 and x2 and x3. And to get this, we're going to use the influence coefficient approach. We're going to be calculating these influence coefficients of Aij, where Aij is the displacement xi due to a unit force at particle j. And along the way, we'll use the fact that Aij and Aji are equal to each other by this idea of reciprocity. What I will do is I will start with an application of a unit force at 1. So what I'm going to do is draw a free body diagram of the system where we have these 3 particles of mass. They're connected by springs. Applying the load here of 1 to particle 1 means that the other force acting on the system from the outside is going to be that spring force, which is Ka11. Keeping in mind that our notations are that this will be the displacement of 1 due to the force at 1, displacement 2 due to the force at 1, and the displacement 3 due to the force at 1. So right away from here, we can see that A11 and A21 and A31 are the same. All 3 move the same. This is not reciprocity, that's just the way that the system moves. So if I sum my forces acting on that system of particles 1, 2, and 3, I have minus Ka11 plus F is equal to a 0. So it says that A11 is equal to F over K, or 1 over K. And then from above, we have, therefore, that A21 and A31, the same thing as A11, so that's 1 over K. And by reciprocity, we have that A12 is equal to A21, and A13 is equal to A31, 1 over K. So with one calculation, we have found what 1, 2, 3, 4, 5 terms in our matrix. This is coming just as a reminder from reciprocity. So now I'm going to move my applied force to particle 2. So what I have here is going to be the FBD I'm going to draw is just going to be of particles 2 and 3. Again, they're connected by this spring. This is 3, this is 2. There's going to be the applied force of unit size there at 2. And then there's going to be a spring force here. But what is that spring force? What we're really doing is, or what we can do, is to replace our system here by this one. This is the spring between 2 and 3. I've got a spring connecting ground to 1 and 1 to 2. These are, this is 2K, I guess, and this is K. And what I want to do is replace this by a single equivalent spring. I'll call that KEQ for equivalent. And we know from the idea of two springs it's in series that 1 over the equivalent is equal to the sum of 1 over the other two. So this becomes 3 over 2K. So the equivalent spring is equal to 2/3 of K. So what this is going to be is the equivalent spring times A to 2. So when I do my force balance, when I sum forces like this for static equilibrium, and keeping in mind that this is A22 and this is A32, then when I sum forces, I'm going to get minus the equivalent spring constant times A22 plus the applied force F is 0 for equilibrium. It says that A22 is equal to 1 over the equivalent spring constant. So this becomes 3 over 2K. Also, we have that A32 is the same as A22. 2 and 3 move the same. And by reciprocity, what we have here is that A23 is the same thing as A32, which we just found. So we now have 8 of the 9 terms. I'm going to now move my applied force. I'm going to move that to 1. So what I'm really looking at here is now I'm looking at the particle 3. I'm sorry, I said 1. I really meant to say 3. So the applied force is here. I'm going to have a spring force acting on this side. I'm going to call it the equivalent spring constant, which we'll derive here in a bit, times A33. What is the equivalent one? Well, it's going to be take our 3 springs to the left of 3, which are K, 2K, and K, and replace that by a single equivalent spring constant. 3 springs is in series. Same kind of thing. The inverse of that is the sum of the other inverses. So that will end up being 5 over 2K. So therefore the equivalent spring constant is equal to 2K over 5. Summing the forces on particle 3 gives us minus K EQA33 is added on to F is equal to 0. So A13 making sure we realize that's a unit force there of F, that's 1 over the equivalent. And so that ends up being equal to 5K, 5 over 2K. So that is our ninth and last term. So therefore, A is equal to 1, 1, 1 across like this. 3 halves, 3 halves, 3 halves, and then 5 over 2 there in the 3, 3 position, 1 over K. And we know that that's the inverse of the stiffness. Let's check. This is one where we can actually check our work. What I'm going to do is write down the potential energy. That's going to be 1/2 kx1 squared. That's the first spring. The second spring there between 1 and 2 is 1/2 2k x2 minus x1 squared plus 1/2 k x3 minus x2 squared. And using our relationship we've derived before, the kij is the mixed partial of the u's with respect to the, or to u with respect to the j's, evaluated at the equilibrium state, will give the stiffness matrix of 3, minus 2, 0, minus 2, 3, minus 1, 0, minus 1, 1 times k. So that's what we would get if we derive k, and to check this, we multiply a times k, a times k, 1, 1, 1, 1, 3 halves, 3 halves, 1, 3 halves, 5 halves, multiplied by k, so it's 3, minus 2, 0, minus 2, 3, minus 1, 0, minus 1, 1, k over k, and sure enough, when we get through, we have the identity matrix. And that's good, because we know that since A is the inverse of K, A times K must be I. So here what we did to find the flexibility matrix, or the inverse of K, was just put the unit force at each one of the 3 locations, and while it's at that, we calculate the displacement of the other 2 particles of mass. We move ourselves from left to right, fill out our 3 by 3 using reciprocity, and then when we got through here, we checked our work to make sure that that was correct.